That picture of the atom you have in your head is wrong, completely wrong. You know, the little ball in the middle with the other little balls going around like planets? Forget it. That's not what an atom looks like. I spent my whole life working with this stuff, teaching it, calculating it, and I want to tell you what an atom really is like and why the story you were told in school had to be a lie. When I say a lie, I don't mean your teacher was evil. I mean it's a cartoon. It's like drawing a cow as a square with 4 sticks. Fine for a 5-year-old, but not if you want a steak. The thing is, that little planetary atom, with electrons going around in neat circles like marbles, is so deeply wrong that it actually blocks people from understanding what's really going on. And what's really going on is much more interesting. Let me tell you where I come into this. For years, I worked on quantum electrodynamics, the theory of how light and electrons interact. That's the theory you need if you really want to understand atoms. I taught freshman physics at Caltech, and every year I'd see the same thing. Bright kids, excited, and all of them with that silly little solar system atom inside their heads. So I had to smash that picture and replace it with something fuzzier, stranger, and in a funny way more beautiful. When I was a kid, I had that planetary picture too. I remember sitting there, drawing the nucleus and then circling little dots around it. It felt so clean, so mechanical. You could imagine turning a crank and the electrons would zip nicely around. Later, at MIT and then at Princeton, when I really learned quantum mechanics, I discovered that nature doesn't care about my nice, neat picture. It doesn't look like that. It doesn't act like that. It doesn't times think times like that. You see, the first lie is that electrons go around the nucleus in orbits. They don't. There are no orbits the way planets have orbits. There isn't even a place where the electron times is times in the way you imagine a tiny bead whizzing around. The whole idea that an atom times looks times like something solid and mechanical is already the wrong question. The question is not, what does an atom look like? The question is, what can we say about what happens when we times measure times an atom? But I'm getting ahead of myself. Let me back up and show you how we got into this mess in the first place. In the old days, if you said atom, people thought of a little hardball. That's Democritus and all that indivisible bits of stuff. Then along comes J. Thomson with his plum pudding model. He says, all right, we've got negative charges, electrons stuck in a kind of positive goo. Imagine raisins in a pudding. That was already an improvement because now you've got parts. But then Rutherford comes along and shoots alpha particles at gold foil, and they bounce back in crazy directions. If matter was a uniform pudding, that wouldn't happen. So Rutherford figures out there must be a tiny, heavy, positively charged center, the nucleus with most of the mass, and the electrons are somehow outside. Now, if you grew up like I did, that's probably the first real atomic picture you heard. A nucleus in the middle, electrons someplace on the outside, planets and the sun. Feels comfortable because we already know about the solar system. Then came Bohr. Now, Niels Bohr was a smart guy. He knew that if the electrons are just whizzing around like planets, the whole thing collapses. According to ordinary electrodynamics, a charged particle going in a circle radiates energy. So your electron should radiate, lose energy, spiral into the nucleus, and boom, atom gone. That's no good, because we're still here. Bohr says, wait a minute. Suppose the electron can only be in certain orbits. Not any old circle, but a few special ones, and in those special orbits it doesn't radiate. It's just there. Quiet. Only when it jumps from one orbit to another does it emit or absorb light in little chunks. That was the Bohr model. Quantized orbits. That was a big step. It explained the spectrum of hydrogen, the lines of color it gives off when you excite it. Beautiful pattern, and Bohr's little formula nailed it. You can forgive people for falling in love with that model. It felt like we'd finally got the atom pinned down. Little planets, special tracks, nice, neat math. When I learned about this as a student, I thought, this is very clever, and then very soon after, I also thought, this is very suspicious, because the theory was kind of half-baked. It said, electrons obey classical mechanics, except when they don't. They radiate like charges, except when they don't. It was like having a car that obeys all the traffic laws except when it wants to jump to another street. The trouble is, Bohr's model worked only times for hydrogen, and only approximately. As soon as you tried to do more complicated atoms, or understand why chemical bonds have the shapes they do, the whole thing started to wheeze and cough. The universe is not built out of hacks that only work on first-year homework problems. So along comes Schrödinger with his wave equation and Heisenberg with his matrix mechanics, and together they smash Bohr's neat little orbits into dust. The idea turns out to be this: the electron in an atom is not a little bead going around. It's described by a times wave function times a kind of mathematical thing that tells you the probability of finding the electron here or there if you go looking. Now, this is the first big shattering of your mental picture. The electron is not in some definite path. All we can talk about is the probability that, if we look, we'll find it in various places. And that probability is spread out in space like a fuzzy cloud. When I started really working with these ideas, I had to train my brain to stop asking, where is the electron times really asterisk? That's the sneaky question. You want to imagine there's a little ball secretly zooming around somewhere, and the wave is just your ignorance. But that's not how it works. The wave is not ignorance. The wave is the thing. If you solve Schrödinger's equation for the hydrogen atom, you don't get circles. You get these funny shapes, these orbitals. The simplest one, the ground state, is a sphere of probability around the nucleus. If you go to the next energy level, there are shapes that look like dumbbells, clover leaves, weird donuts with a hole in the middle. If you could actually times C times the electron cloud, it would look like a three-dimensional fog, thicker in some places, thinner in others. Let me give you a mental picture that's closer to the truth. Imagine you're standing in a dark room and someone is throwing a dart at the wall over and over, but you only see where it sticks each time you turn the lights on for a split second. After a while you start getting a pattern, more holes here, fewer holes there. Pretty soon you can see a shape emerging from the statistics. That shape is your orbital. The dart isn't following a nice neat oval. It's hitting all over, but with different probabilities. In quantum mechanics, we don't even talk about the dart having a definite path between one hit and the next. We just talk about the probabilities. That's the basic rule. When I worked out my path integral formulation later, I made it even crazier. The electron doesn't take times one times path, it sort of takes times all possible paths times at once, and they interfere. But in the end, the result you can compare with experiment is still just probabilities. Now here's the interesting part. People always ask, well, but what does an atom times really times look like? If I could shrink down and look at one, what would I see? And the answer is, you're asking for something nature doesn't provide. To see an atom, you need light photons. But the wavelengths of light that are small enough to probe something the size of an atom are so energetic that when you shine them in, you knock the electron around. You don't get to peek without touching. This is not a technical difficulty. It's not that our microscopes are just a little too crude. It's that the act of looking is part times of what happens. If you try to look very precisely at where the electron is, you necessarily give it a big kick. That's Heisenberg's uncertainty principle. You can't know both the position and momentum very accurately at the same time. The more closely you pin down one, the more you fuzz up the other. I used to tell students, imagine trying to see a tiny bug on the surface of a pond by throwing bowling balls at it. Every time you see it, you've already messed it up. That's more or less what we're stuck with at atomic scales. So this dream that there's some definite picture of the atom sitting there, and we're just too clumsy to see it, that dream is wrong. The fuzzy wave, the probability cloud, asterisk, that's times the closest thing you get to what it looks like. Once, at Caltech, I was giving this big freshman lecture, and I drew the usual little planetary atom on the board. Then I crossed it out very hard and said, this is a lie. If you see this in a book, it's a lie. The students laughed, but I meant it. Then I started drawing blobs, S, orbital, a round blob. P, orbital, two blobs like a dumbbell, D orbitals, four-leaf clovers and donuts. I told them, these are not the paths of the electron. These are the maps of our ignorance and our knowledge. This is where the electron is likely to be if you look. Some smart kid in the front row raised his hand. I can still see his face, and he asked, "But Professor Feynman, where times is times the electron before we look?" And I said, "Nobody knows. I think I can safely say that nobody understands quantum mechanics. We can calculate what happens when we do certain experiments. We can match the results to 12 decimal places. But if you ask me to tell you a story about what it's doing in between, I don't have one that matches the math and also sounds like everyday experience. Now, I want to show you why the Bohr picture is not just a little bit wrong, but deeply misleading. In that model, the electron is like a planet, and the energy levels are like different ring roads. You jump from one ring to another, you get light. Fine, but real atoms don't just sit there as little solar systems. The electrons in multi-electron atoms repel each other. They occupy these overlapping orbitals, and the shapes of those orbitals determine the whole structure of chemistry. Why do carbon atoms like to make 4 bonds in a tetrahedral shape? Why does oxygen like to make 2 bonds? Why are there noble gases that hardly react with anything? You can't explain any of that with little planets. You need orbitals with different shapes and energies, and you need the Pauli exclusion principle that says you can't stuff too many electrons into the same quantum state. When you solve the equations, you find shells and subshells sp, df stacked up in energy. You get these beautiful patterns, 2 electrons in an s orbital, 6 in p, 10 in d, and so on. The whole periodic table, with all its regularities and oddities, comes out of the shapes and energies of these fuzzy clouds. That's not just a cute picture. That's real, testable stuff. We measure ionization energies, spectra, chemical behavior. They all line up with these quantum mechanical orbitals. So the question is, which is more real? The picture that looks like what you expect from big things, planets and balls, or the one that actually predicts the experiments, right? For me, the answer is obvious. Nature doesn't care what time seems, time's intuitive. It just goes ahead and does what it does, and what it does at the atomic level looks like waves of probability. Let me tell you something else that bothered me for a long time. In our ordinary lives, things are pretty definite. This glass is on the table. It's not smeared out over the room. You don't wake up half in the kitchen and half in the bedroom. So where does this fuzziness go when you go from atoms to apples? If atoms are fuzzy, why aren't we? The thing is, the fuzziness is still there. It's just that when you have zillions and zillions of atoms together, all interacting and bumping into each other and with the environment, the quantum phases, the little wiggly parts of the wave function get scrambled up in such a complicated way that the probabilities for big things end up being sharply peaked. You can approximate times them as definite. We call that classical behavior. It's an approximation that works extremely well when you're big and fat and made of lots of atoms. But down at the atomic scale, you can't ignore the fuzz. One of my favorite tricks when thinking about this stuff was to imagine shrinking myself down. People always ask, if I were small enough to stand on an electron in an atom, what would I see? I say you'd see nothing, because the whole idea of standing on an electron makes no sense. There is no little billiard ball there with a surface you can stand on. There is just this cloud, this pattern in the chances of where you'll find a click in your detector. It's very tempting to try to outsmart nature. Maybe there's some hidden variable that says where the electron really is, and the wave is just our ignorance. People tried that. They wrote whole papers saying, we'll put little arrows behind the scenes, and so on. But when you work out the consequences, you find you can't do that without giving up something else you care about, like locality, or the idea that causes come before effects in a normal way. Experiments with entangled particles, Bell's theorem, and all that make it very hard to keep the old classical picture. You might say, all right, but can't we at least draw times what an orbital looks like? And here at last we can give you some satisfaction. If you take the Schrödinger equation seriously and solve it on a big computer, you can draw 3D pictures of the electron probability clouds. People have done that little colored blobs in space, showing where the electron is likely to show up if you look. If you want something to put on the cover of a textbook or on the wall of your dorm room, that's your honest picture of the atom, not balls whizzing around, but overlapping fuzzy shapes. I remember the first time I saw those computed orbital shapes. I thought, this is terrific. This is what we should have been drawing all along. But then I realized something else. If you just show the blobs without explaining the rules, people will misunderstand times those times too. They'll think, oh, the electron is a little ball smeared out over all these points at once. That's also not quite right. The wave function is not a physical mist out there. It's a tool for calculating probabilities. It's a kind of abstract thing. The thing that's out there is, well, whatever it is that keeps making our detectors click the way the theory says. One of the best habits I learned early was never to fool myself. My father taught me that. When I was a boy, he'd take me for walks and show me birds and say, you can know the name of that bird in all the languages of the world and still know nothing about the bird. Watch what it does. Later in physics, I learned the same lesson. Don't get too attached to the times, names, times, or the times pictures asterisk. Watch what the equations do. Compare with experiment. That's the only real judge. So when I tell you that the planetary atom is a lie, I'm not just being cute. I'm trying to save you from being stuck with a picture that doesn't let you ask the right questions. You see, once you accept that the atom is fundamentally described by probabilities and not by little beads on tracks, a lot of other things fall into place. The stability of matter, the patterns in chemistry, the properties of solids and metals, it all comes out naturally. And there's something else I like about this fuzzy probabilistic picture. It's honest about ignorance. It doesn't pretend that the universe is a clock where, if you just knew everything exactly, you could predict everything forever. At the atomic level, there is built-in unpredictability. You can say, there is a 30% chance the electron will be here, 70% there, but you cannot say which it will be in a particular trial. That's not because you're stupid or your instruments aren't good enough. It's because that's the way the world is. Some people don't like that. They say, God doesn't play dice, and so on. I never understood why they thought they could tell God what to do. The evidence is that, at small scales, nature behaves like it's rolling dice all the time. Very precise dice with well-defined probabilities, but dice just the same. Personally, I find that wonderful. The world is not just a frozen, predictable machine. It's dancing. Let me give you one last twist. When we say, you can't really see an atom, it sounds like a limitation. Oh, too bad, we'll never get a picture. That's not the right attitude. The fact that we times can't times get a sharp picture that the best we can do is this dance of probabilities that's telling us something deep about reality. It's not a failure of our imagination, it's a feature of the universe. I like to think of it this way. Suppose you're a little kid looking through a keyhole into a room. You see people walking by now and then. You might imagine the room is just a corridor because that's all you see. Then one day, somebody opens the door and you discover the room is big and full of furniture and people doing all kinds of things. Quantum mechanics is like that door. It shows you that underneath the neat, solid world you think you see, there's a much more complicated probabilistic dance going on. You might ask, well, do we now times understand times the atom? And I'd have to be honest and say we understand how to times calculate times what happens with atoms very, very well. We can predict spectra, chemical reactions, all sorts of things with fantastic accuracy. But if by understand you mean having a picture in your head like a little machine where you can say, ah, yes, the gear turns this way, that pushes this, and so on, we don't have that, and maybe we can't. I once said, I think I can safely say that nobody understands quantum mechanics. People like to quote that as if it means we're all confused and the whole thing is a mess. That's not quite right. The theory is crystal clear mathematically and works great. What we don't understand is times why times the world is that way instead of some other way that would be more comfortable for our classical intuition. So if you want to adjust your mental picture of the atom, here's what I suggest. Take your little solar system model and blow it up. Kaboom! Keep the nucleus. It's still there, a tiny, heavy, positively charged clump, but throw away the neat little orbits. In their place, imagine a sort of ghostly three-dimensional cloud around the nucleus. The cloud is thicker in some regions, thinner in others, depending on the energy level and the type of orbital. That cloud doesn't spin like a wheel. It just sits there, representing the odds. If you insist on some motion, remember my path integrals. The electron goes on all paths at once, and these paths interfere to give you that standing wave pattern, the orbital. It's like a guitar string, not a planet. The electron is in a standing wave pattern around the nucleus. Different notes, different shapes. And whenever you measure, whenever you interact with the atom in a way that can tell you where the electron is, you get a single result, here or there. Then the wave function, which was spread out, collapses to reflect the fact that now you times know times where it is. A moment later, if you let it go, the wave starts spreading again according to Schrödinger's equation. Measurement, spread, measurement, spread, that's the rhythm. The beauty of the whole thing for me is that it forces us to be humble. We'd like to think that if we're smart enough, we can picture everything as little gears and balls. But at the atomic level, nature refuses to fit into that box. It says, I will give you probabilities, not certainties. I will give you patterns, not paths. Take it or leave it. So that's what an atom really looks like. Not a miniature solar system, but a mathematical object whose visible shadow is a fuzzy cloud of probability. You can draw that cloud, you can calculate its shape, you can use it to build lasers and transistors and all the fancy toys of modern life. And you can sit back and feel a little awe that all this solidity around you is built out of something so inescapably uncertain. If you walk away from this with anything, I hope it's this. Don't be satisfied with the neat little pictures they give you in school. Ask, does it actually match what we see in experiments? If not, be ready to throw it out, no matter how comfortable it feels. The pleasure, the real pleasure, is in finding out how nature actually behaves, not in forcing her to live in your imagination. And if your mental picture of the atom is now a little shattered, good. Sweep up the pieces, keep the nucleus, and let the electrons float back as a cloud of possibilities. That's closer to the truth. It's messier, it's stranger, and it's a lot more fun.